Hello there. In this video, we'll be learning how to get the limits of exponential functions. To do this, we first note that exponential functions are continuous everywhere, since the domain of exponential functions are just all real numbers. Now, this is nice since we'll actually have two nice properties associated with this. So first, if f is continuous at a point A, then it follows by the definition of continuity at a point that the limit of f of x at that point is equal to the value or the function evaluated at that point. Next, if f is continuous at a limit of a function, then it follows that the limit of f of g of x as x approaches a is equal to f of the limit of that function. So basically, we can move this function f outside of the limit. In this case, we can move the exponential function outside of the limit and solve for the limit inside first instead. So we'll be using these two properties later on in our examples. But first, as an illustration, a simple illustration of these two properties. Oh, by the way, for this second property, this was obtained by a theorem on the composite limits, which I also have a video in the past on that one. So yeah, again, for the illustration, let's have this first one. We have the limit of e raised to x as x approaches a. If you don't know, e out here refers to the Euler's constant, so you may check that one up. But basically, this is often used when dealing with exponential functions. So if we are to solve this one, since we know that the exponential function out here is continuous everywhere, this means that for this point A, we can simply just plug that one in by our first property mentioned above. So we'll have here e raised to a. So that answers this first limit. Let's have this second one. We have the limit of e raised to g of x as x approaches a. Since we know that e here is continuous, the exponential function is continuous everywhere, then we can factor out e in this limit, or that is, we'll have the exponential of the limit of g of x as x approaches. Or to write this much better, we can write it as the exponential of the limit of g of x as x approaches a. So these two are the same. So that illustrates our two properties that we can use later on. And aside from this, we'll also be discussing one more thing that is very useful in our calculations. So yeah, let's have this one. And in general, we let f of x be equal to a raised to x, wherein a is positive and a is not equal to 1. So this is just a basic exponential function. And given this, we'll actually have two cases. Either a is greater than 1 or a is between 0 and 1. For the first case, its graph would look something like this. So it is an increasing function. For the other one, for the case 2, its graph would look something like this. Now a decreasing function. Now, given this, let's try to find the limits at infinity of these two cases. For this first case, as x goes to infinity, it would look something like this, so this area. And clearly the value out here goes to infinity. Now for this next one, as x goes to negative infinity, this area out here, it goes to 0. So these are the two limits at infinity for the first case. For the second case, as x goes to infinity, this area out here, the limit approaches 0. Now as x goes to negative infinity, this region out here, a raised to x goes to infinity. And so these are the 4 things that we also need to remember, as this would be useful in our calculations as well later on. So again, you need to remember the 2 properties mentioned earlier and these 4 limits out here. So now let's try out some examples. So we have here 3 examples that you can try to work on first on your own. Okay, good. So let's start with the first example. We have here the limit as x approaches 2 of 2 raised to x plus 2. So in here, again, take note that 2 raised to x plus 2 out here is continuous everywhere, since 2 is just constant. So it isn't dependent by x, so it is continuous everywhere. And then 2 raised to x out here is exponential. So combining these two, we have a continuous function out, continuous everywhere. This means that by definition of continuity at a point, or the first property mentioned earlier, we can simply plug in 2 into the given function. So we'll have 2 squared plus 2 out here. 2 squared is equal to 4. Add these 2 up and we'll obtain 6. So as simple as that. That answers the first limit out here. So good. Let's move on to the second example. We have here the limit of e raised to x squared plus 2x plus 1 as x goes to 0. So how do we solve this? We take note that the exponential function is continuous everywhere. This means that by the second property mentioned, the composite limits theorem, so we can move this exponential function out of the limit. That is, we'll have the exponential of the limit as x goes to 0 of x squared plus 2x plus 1. And we can instead solve for the limit inside first. Solving for this limit, since this one is just a polynomial, so we can simply plug in 0 into the function. That is, we'll have 0 squared plus 2 times 0 plus 1, or simply, so this one will just be removed and we'll be left with the exponential of 1, or e raised to 1, or simply just e. That answers the second example. So far so good, I hope so. And now let's move on to the last example. We have the limit of 2 raised to x plus 5 raised to x over 10 raised to x as x goes to infinity. Observe that if we plug in infinity immediately into the function, we'll have infinity over infinity, which again is an indeterminate, so we can't really conclude anything from that. So to answer this, we still need a little bit of manipulation in this one. What I'll do is I will split this fraction into 2. That is, we'll have 2 raised to x over 10 raised to x plus 5 raised to x over 10 raised to x. So this is simply just by properties of fractions. And then here, observe that by laws of exponents, since we have a common exponent of x, we can factor that one out to obtain 2 over 10 raised to x plus 5 over 10 raised to x. We just simplify the fraction inside to obtain 1 over 5 and 1 over 2. And take note that these two are less than 1. So if we recall earlier, the one with the graph, so if we have a raised to x, wherein a is between 0 and 1, and as x goes to infinity, what happens to this function? Recall from earlier that this function goes this function goes to 0. So we have here 0 plus 0, or simply just 0. And so that answers the last exam. So it's pretty straightforward, and I hope you got these examples correctly. But if not, you may rewind the video and check again the solution or the process and how we obtained and arrived with the correct answer. To end this, here are 2 exercises that you can work on. Now, these 2 exercises are quite not straightforward, unlike the first 2 examples. But as a hint, for this first one, what you'll do is you'll be needing to multiply a certain factor out here. Since observe that if we plug in negative infinity into the function, we'll have an indeterminate. So we need to multiply a suitable factor out here. For this next one, observe that if we plug in infinity into this function, this one approaches. Actually, it's not easy, or we don't have any conclusion, since if we plug in infinity out here, this part out here will be infinity minus infinity, which is an indeterminate. So what to do to answer this? Now, as a hint, what you'll do is you'll be factoring a certain factor out here. So this part out here would be equal to a certain factor times the expression that is left. And then from this, you can evaluate the limit, since the limit out here would just be, I think like 1 something. Yeah, I think that's how it would look like. Let me see. Yeah. So yeah, I hope you can try to work on these exercises, and you may comment down below if you have any comments, suggestions, or even answer solutions regarding this exercise. So yeah, that's it. I hope you enjoyed this one, and yeah, that's all for this video.